Okay, so welcome to class 17 of CH 576. Just to recall what we are doing in the last class, we are dealing with this expression of heat capacity. I hope you remember. This
Yes,
is
sir.
the one. You have an integral, of course, you have some constant sitting there. And I had showed that if you go to high temperature limit, then this expression exactly matches that of with Dulong and Petit's, which is 3 times nkb. Okay, because you have this 3 nkb times 3 by this beta h cross omega d whole cube, and this is integral. This I'm calling dy function, and this is a function of theta d by t. Theta d is called d by temperature. And I showed that in the limit, when your temperature is very, very large, your dy function is equal to 1, because you can then expand. This is an integral like x to the power of 4 exponential of x by exponential of x minus 1 whole square. This one's exponential terms you can expand. The numerator you can actually approximate this as 1, because you can neglect this denominator. This x you keep, and this one minus 1, they'll cancel. They'll give you x square. So x to the 4 by x square gives you x square dx, which is x cubed by 3. And if you put the limit, then it will exactly cancel the prefactor and give you equal to 1. So it essentially tells you that, okay, my expression of the cv becomes 3 nkb times fd at high temperature. This fd at high temperature is 1. So it exactly matches one expect using equipartition theorem. This expression is also known as Dulong and Petit's law, 3n kV. Okay. So, but what happens at low temperature, and that is very important and interesting. Actually, what happens at low temperature, and we'll try to do low temperature thing today, and we'll see what happened at low temperature. Now, if I say this is low temperature, uh, what does it mean? New temperature in what respect? So basically, it is in the limit that your, if I take this beta is large, actually beta h cross omega is much greater than 1. This is low temperature, isn't it? Because this is h cross omega by kb t is much greater than 1. Okay, because 1 over very small is very large. Is it fine? So if it is so, then obviously when your omega is actually a little cut off, because you will be omega is must be less than equal to omega d, and the integration limit, you remember cv had expression like whatever, some kb times many constants you had, and then you have integral like from 0 to, remember, beta. Can you tell me what is the limit of integration? It was beta h cross omega d. Check your, yeah, notes, and your expression like x4. So in the limit, when temperature is low, the upper limit goes to what? Can anyone tell me? Because you first you remember that what was the expression for this sigma omega? You remember the Debye frequency? You remember, na? Because you're because you're because you're in the limit when omega is less than omega d, isn't it? Because you're using this expression for sigma omega, no?
Yes.
Otherwise, sigma omega is 0. So
Yes.
this upper limit goes to 0, sorry, infinity, when the temperature is high. Okay, Anish, high temperature
Yes, sir.
should be straightforward. So if it now, it is what, this is an uh, actually integral. You are putting limits, the definite integral, no? and this integrand is such it will not blow up. So what do you expect? This result, you expect this to be equal to constant, no? Or you carry out the integration. I am not carrying it out, but if I can carry out the integration, I should get something like constant. Is this clear? That I'll get constant there.
Yes, sir.
So I'll get constant. So if I get constant, and if you go back and check your expression, check your expression for the free factor. You remember the free factor? I don't know. You have KB, of course. You had KB. You also had.
4 minus 3.
I'm just writing constants for a reason. But you divided by, you remember what was that?
Beta cube. H cube.
Beta h cross omega cube kind of thing is there. So basically you had something like your CV is proportional to 1 by beta cube, which basically means, is it, at high temperature? Are you convinced?
Yes.
And this is called T cube law. Maybe you must have heard about it, because if you and it is experimentally verified for many solids that if you can go to high temperature, your CV is proportional to T cube. So actually I don't need to do the integration. No,
Low
don't.
temperature.
Yeah, I do not. Sorry, low temperature. Yeah, I must be very careful. At what happens at low temperature, high temperature? Sorry, low
3
temperature.
kb.
Yeah. So and CV is 3N kb at high temperature. Independent of temperature, essentially, isn't it? So basically, if I plot CV, how does it look like? So I know that if I plot CV and divided by 3N, say I divided by say 3N kb, and if I would if I plot molar heat capacity, then this N is Avogadro number. So actually, you're dividing by 3 times R. So if this is 1, then eventually in the high temperature limit, here it will be 1, isn't it?
Yes, sir.
But the profile is like that. It is hand drawn. So here you will see that the growth when the temperature is low is PQ. And this is your Dulong and Petit's result. Okay. So it and your Debye heat capacity expression gives you the same scaling at you as you get from experiments. If you are very particular about integration, if you carry out all the integrations and you put the expression, so I'm just writing down the final expression. No, don't need to remember, because I don't. Good to remember that it is T cube, but there is no need like Cs by H cross. No need to remember this expression. So this is the final expression. Okay. But while doing that, this integral I am calling it I. This I. This integral I, actually I'll tell you what is this integral when your temperature is low, basically, then only the integration limit is 0 to infinity. And the value of this integral is rather 4. You can check this. And this is not very easy integration to carry out. Okay. Because if you see, this integration is like this. You can actually simplify this integration as x cube divided by, from here you can go there, and then eventually you can show this is equal to this. Okay. How can you show? You can just check this book by Friedrich Reif. Have a look. Because I don't think many of you, I think many of you do not know this complex analysis, isn't it? Contour integrals. So I'm not doing this. But if you are interested, you can go and check this book. If you don't understand, come back to me. Okay. And I'll show you some values of this theta d. Theta d is, for example, for if I take sodium chloride, theta d is 308 in Kelvin. Um, Potassium chloride, it is 230, something like that. And many ways you can calculate theta d. Uh, One, you can calculate from either you calculate from specific heat, or using elastic constants of the solid. I am not going into that. I'm just giving you some information. Okay. But what is important here is that low temperature, it grows as T cube. High, very high temperature, it saturates to Dulong and Petit's result. Is this clear? Debye.
Yes, sir.
Actually, before Debye, Einstein also did something. How many of you know there is also a version of Einstein's heat capacity? So we'll just briefly mention this.
Yes,
This is
sir.
much simpler. This is uh, I think it is taught, no, in somewhere in chemistry. I don't know in which course, but Einstein heat capacity and Debye heat capacity is at least mentioned. Maybe in a course dealing with solid state chemistry. Okay, what was Einstein formulation? Einstein's formulation was much simpler. So he had what is known as n number of non-interacting uh, independent harmonic oscillator. Okay, and each with frequency omega. Each of them have same frequency. Okay, this I write frequency, but actually it's angular frequency. Okay, is this clear?
Yes,
Now,
sir.
can anyone tell me what should be the heat capacity expression? So let me go back. If you go back to Debye heat capacity expression, it was like this. General heat capacity expression. Not Debye, even the general one. This is general, no?
Yes.
But uh, in the normal mode picture, isn't it? We have 3n number of normal mode.
Yes, sir.
Now here I have n harmonic oscillator. Each can oscillate in 3 directions. So we have 3n oscillations, independent, each with omega. Okay. So what will happen to this Einstein? But you don't have this kind of thing, sigma omega d omega for Einstein. There is no we don't say that there are oscillation with frequency omega and omega plus d omega. A number of oscillators within the frequency range is sigma omega d omega. We don't say that, okay? Because all are having same uh, frequency. So actually, how many oscillators are there? 3n, isn't it? So I should have 3n of this. I should have kb, and I should not have this integral, isn't it? This integration rather, and I should only have the grand, isn't it? Without this sigma omega d omega. Can you get it? Without
Yes.
this. So actually you should have something like uh, beta h cross omega whole square exponential of beta h cross omega exponential of beta h cross omega minus 1 whole square. Now this one I can write slightly different way, because since I'm doing it a model, I'm calling it Einstein's model. So I can write beta h cross omega as, I hope you remember, understand, some theta e divided by t whole square exponential of theta e divided by t divided by, I hope you understand. What is theta e?
H cross omega by kb.
And I can call it something, since I put e, you know what is this? This is called Einstein temperature, like Debye temperature. But all the harmonic oscillators have the same frequency. So this is the expression. Now, if I go to the limit when t is going to infinity, what will happen to this expression, Einstein expression, CV? Can anyone tell me? 3n kb. T is infinity, no? What should I do to the exponential term? You have done it many times.
1 plus theta by d divided
Yes,
by.
I just expand, because it is 1 over t, so t is very large, 1 over t is very small. So what is happening now? What is the
3n
expression?
kb.
3n kb. See, this is, you have theta e by t. Okay. Now this one I can just neglect. No, this part, this one, and this will cancel. So what I have here, of course, this is approximately equal to. So you are convinced? And this is
Yes, sir.
nothing but again Dulong and Petty's law. So the high temperature limit is okay. Is achieved. It is consistent with the high temperature limit. What happens to low temperature? What happened to low temperature?
You took by the limit tending to 0.
Low temperature. Let us do it as if t goes to 0, or in other words, theta e by t is very, very large, isn't it? So your
Yes.
expression now becomes CV. You have 3n kb is there. Whole square should be there. You have exponential of theta e by t. I keep it like this. But in the denominator, you had what? You look at it, you had theta exponential theta e by t minus 1 whole square. Now exponential of theta e by t has to be very large, because your t is very, very small, isn't it? So in the denominator, I should have only one term. Minus 1 I can neglect. You understand, no? Because essentially you have this.
Yes.
That is equal to, okay, and that is what I'm going to do. This is 2. So what I'm going to get now? Exponential of minus, but it is not t cube. And experimental you get t cube, so it is not a very good model. It does not give you that at low temperature this t cube law. Okay, and if you plot this CV, sorry, again I'm drawing with hand, CV divided by say n kb, or you can also divide by 3n kb. This is also fine. Then you'll see that both the models will go like this. This is your one, okay, at high temperature. But the low temperature, one model is Debye, which gives you T cube, which is the upper one. And this is Einstein, which is 1 by T square exponential of minus theta E by T kind of behavior. Okay, this is Einstein. This is Debye. And experimental one is very close to Debye. But again, it is not exactly with Debye, because Debye also has this approximate way of calculating this sigma E, number of states within frequency omega and omega plus d omega, d omega rather. That is done approximately. So ideally, one should do a quantum mechanical calculation in order to find uh, in order to find the right answer. Okay, and that is done nowadays on computer, so you can model it on a computer, the heat capacity of solid. Okay, so now I'll move to another topic now. So you must have realized that I have entered into a system of interacting particles, because here the one I just discussed is also interacting particle, isn't it? So there is something like hydrogen atom problem of quantum mechanics. The hydrogen atom problem of quantum mechanics is actually a problem which is exactly solvable. No? Even particle in a box is also exactly solvable. So like the most celebrated exactly solvable model in statistical mechanics is called Ising model. So how many of you know? I don't know, but I may ask. How many of you heard about it? It's the Ising model.
I have heard, but not understood.
Okay, that's fine actually. So Ising model was solved by a person called Ising, who was a PhD student of a physicist called Lenz. Not the Lenz you know, not that famous Lenz, some other Lenz in physics. And he solved this as a part of his PhD problem. Okay, as a part of his PhD problem. So I solved it long back, I think 1920s. So I'm just trying to find out the year. I don't remember right now. And then I'll introduce the model. Yeah, it is 1925. So it's solved in 1925. What is this model? The model is as follows. I have, this is in one dimension, first of all. So Anish, did you know about Ising model? This BA student?
I have heard of the name being applied in several uh, lattice models and other things, but I've not read it in detail.
Okay, so let us do it. So I have sites like this, and each site has a spin. So all sites are occupied. So each site, okay, what I say, rather than saying like this, I can call it a chain of uh, a linear chain of n spins, and each of these spin could be in two states. Two states, okay. One is plus, which is spin up. Other one is minus, which is spin down. Okay. In addition, you have an external magnetic field. We have an external magnetic field. And also, these chains are these spins are such that we consider only nearest neighbor interactions. This is very important. Basically means if I have ith spin, then ith spin will interact with I plus 1 and with I minus 1. Okay, so if I have a spin here on this side, say, forget about the spins which are at the boundaries, but if I take this spin, for example, this interacts with this one, this interacts with this one. Is this clear? The picture, at least qualitative picture, is clear. The model. Tell me if you have any
Yes, sir.
queries.
Yes, sir.
It's very simple. The statements are very simple. So what will be the next step? Can anyone tell me what should be the next step? Next step would be to construct the Hamiltonian. No? See, the steps are very well known now. Construct the Hamiltonian, then construct the partition function, and then calculate the thermodynamic quantities, isn't it?
Yes,
So
sir.
let us write down the Hamiltonian. I'm calling it H. So I'm calling this spin, say ith spin, I'm calling it sigma I. So interaction is such that sigma I times sigma I plus 1. How many such i's are there? You know that there are n, isn't it? N. And also I multiply this with the strength of interaction, J, and by convention I put a sign minus there. And J is also greater than 0. Interaction strength, okay? If I have only this in the Hamiltonian, just physically try to see J greater than 0. Now if both the spin sigma I and sigma I plus 1 both are up, if both are up, say one of the configurations, the sigma 1 and sigma 2 both are up, then what will be the energy? I have two chain system. This will be minus J into, now sigma can have two values, sigma I could be plus 1 or minus 1. So it will have value minus J, isn't it? 1 into 1. Or both are down, what will be the value?
Minus.
Minus 1 into minus 1. So this is minus J, this is also minus J. Okay. So there, and J is positive, so some negative quantity. So as if you have a reference which is 0, it is below 0, that reference you can think of. So essentially your energy is lowered, isn't it?
Yes, sir.
And with J positive, this kind of Hamiltonian will try to, so essentially what you expect, that if all the spins are aligned parallel to each other, all are parallel, either all are spin up or all are spin down, that state is favored, isn't it? If I just look at this expression, and that is called
Yes.
ferromagnetic state. This is a ferromagnetic state, isn't it? From the expression looks like that it is favored. Ferromagnetic state is favored. Clear?
Yes, sir.
So all spins are up or all spins are down. Okay, but then you also have another uh, term in that Hamiltonian, which is something like some strength of magnetic field times sigma I goes 1 to n. Here also you have a minus sign, because if you have a magnetic field in this direction, which is this is the strength of the magnetic field, which is equal to h, which is the magnetic field times mu, this magnetic moment. This is the strength of interaction. This is the strength of the magnetic field, and this is mu. Mu is the magnetic moment. So this is your Hamiltonian. Sorry, convince that this is your Hamiltonian. That is very important. External
Kinetic energy.
magnetic field. Hmm. Yeah, tell me.
Uh, uh, this model does not account for kinetic energy, does it?
No, no, there is no kinetic energy in that sense. There's a spin system. No, it is just like
Yes.
quantum mechanics,
Okay.
like quantum mechanics of spin. But these are classical spins, of course. These are not quantum mechanical. But I can have only one degree of freedom, which is spin, which I'm calling spin. It should be up or down. There is no mass or anything. There is no kinetic energy in that sense.
This is like spin Hamiltonian.
This is spin Hamiltonian.
Okay.
Yes, it's just like spin Hamiltonian. So this is nearest number interaction, the first term, isn't it?
Yes.
Okay. So then what should I do? I should now calculate the partition function, the canonical partition function. Let us calculate the canonical partition function. Calling it Q, function of n, b, and t. Can anyone tell me what is the expression? Now you should be able to see.
Sum
Write
over
down
j
it.
e power minus beta
Okay.
h.
Basically, there should be a sum, and then I'll have exponential of minus beta times h, isn't it? This h
Yes.
has minus, no? So it will, I can just put it plus. Huh? Fine?
Yes.
This is fine.
Yes.
And then I have something like j sigma I plus 1 plus b sigma I. This is how it is, no?
Yes.
What about the sum? Now this, you have to understand that sum is, whenever you calculate partition function, sum is over all possible arrangements, all possible microstates, isn't it? All possible configurations, isn't it? I use all these terms. What does it mean? It basically means think physically. In one, I have many such snapshots, isn't it? Possible that many ways I can put this n number of spins on this linear chain. Okay.
Yes, sir.
So basically, but this spin could be either up or either down. So actually, I have to sum over all possible spins. How many spins are there?
N.
Sigma 1 to sigma n. And each spin can have two values, plus 1 or minus 1. So actually, I can say this is, you understand, no? For each spin, I have two states. So this is your
Yes.
partition function. Is this clear, all of you? That it is your partition function? Should be clear.
Yes, sir.
You are all only saying this. Kailash, can you follow?
Yes, sir.
Yeah, so this is a partition
I'm
function.
following.
Now we had all these pin on a line, but in order to evaluate this partition function, we'll do a trick, and from a line we'll go to a ring or circle. In other words, we'll put a periodic boundary condition. Okay, what does it mean? It basically means when I reach n plus 1, so if I go beyond n, so I put another sigma n plus 1, but that has to be equal to where I start, sigma 1. You understand this? Mathematically means this, sigma n plus 1 is equal to sigma 1. So my n plus 1 spin is nothing but my first spin. I come back on a loop. So I start like here, this is number 1. This is one configuration, maybe some are up, some are down, like this. And say this is my sigma n, this is sigma n minus 1. The next one should be my, so this is sigma 1, no? My sigma n plus 1, this is equal to sigma 1. You understand what I am saying here?
Yes, sir.
This
Yes,
is
sir.
not very difficult. I am just putting periodic boundary condition. Now, if I put this periodic boundary condition, then you will see that the partition function is written like this. This n is not mentioned because you have periodic boundary condition, but you know there are n spins, q, b, comma, t, and this expression is going to change a little. So I have expression like this, sigma 1. I'm not writing plus minus 1 equal to, because you know, okay, just not writing. Okay, well, maybe I'll write it in the next page, because so my expression for the partition function is sigma 1. Of course, it is plus minus 1. I'm just lazy, I'm not writing the values. I should have beta. Beta is common, no? J is there. This is I and I plus 1 plus B. Now here, what you had earlier, you remember? You had sigma I, Anish.
Yes.
So now I am just divided by 2 and putting, because of this periodic boundary condition. And I can write this. Just try to convince yourself. I go back. What I had
Yes,
b
sir.
times summation sigma I. That one I have replaced by b by 2 times sigma I plus 1 because of this periodic boundary condition. It is very difficult to convince yourself. You can just go and convince yourself.
Yes.
Okay. And the next I can use the fact that I have an exponential here. You know that exponential of a sum is actually product of exponentials, isn't it? So your
Yes.
q b comma t is, I can this collectively this write it as, and then I write as a product of this. Okay, and what I have, the expression is exponential of beta j sigma I sigma I plus 1 plus b by 2 sigma I plus 1. Fine? Are you happy
Yes,
with
sir.
it if I write it like this? And now look at it, this part, this expression, I am writing it as m sigma I plus 1, and these are actually, this is like, these are matrix elements. Okay, so my expression for q has become now what? My expression for the partition function now has become sum over all spin arrangements, then product of this okay. This is fine. Now what are the possible matrix elements? Just look at it. What are the values of sigma?
Plus or
Values of
minus.
sigma are either +1 or -1. So basically this is a matrix element of a 2 × 2 matrix, which is M, isn't it? And so I can actually think of a 2 × 2 matrix. What happened? Yes. So I can think of a 2 × 2 matrix, which I'm calling M, and we'll have how many terms are there? Matrix elements 4. With matrix elements. Can anyone tell me what are these matrix elements? What I have here, just see what I have here. Can anyone tell me what are these matrix elements? We'll come to that in few minutes.
If we substitute sigma I sigma I plus
So
plus one,
basically you will have terms like m plus plus, both are plus, m minus minus, m plus minus, and m minus plus. Will come in few seconds. So let us deal with this. So if I expand this, so I have something like sigma 1, sigma 2. This is very important what I am doing. You will not find it in a book done in so much detail. So Anish, Kailash, Pooja, whoever is there, Nashit, I'll have terms like this: sigma 1, sigma 2. What is the next term?
sigma 2, sigma 3,
Sigma 2, sigma 3. What is the last term? Sigma n,
and sigma
sigma
1.
n plus 1, but because of periodic boundary condition, I have sigma 1. This is fine if I write like this.
Yes, sir.
Yes, sir.
Now the matrix element, this, if you have done a course in linear algebra, I'm sure people who have taken quantum mechanics or in other context, at least people who have taken my 4 to 5, it will be very useful that this matrix elements, you know that you have done it in quantum mechanics, no? That matrix elements say Hij. How do you write? Use some basis and you write. So this matrix element also you can use the basis sigma I, and this one you can write it as your m sigma I plus 1 is nothing but your sigma I, the matrix I'm talking about, this, This fine? Is this fine?
Sir, could you explain what you have
Yeah,
written
so
here?
I'm saying that m sigma I plus 1, the one I'm written here, you can actually express as a matrix element. This is a matrix element, no? And you can express this in the basis. The basis is this sigma I. Sigma I is the basis. Like quantum mechanics. Like quantum mechanics, what do you do in quantum mechanics? Go back to your PH 107. Matrix representation of operators. You remember? You remember matrix representation of operators. I have an operator A, and the matrix representation of this operator is A11, A22, A12, A21. Like a simpler case, 2 cross 2 matrix. Actually, in general, you have n cross n matrix, isn't it? Remember?
Because of that.
Yes. When A11 is something like psi 1A, psi 1. Remember this? A12 is Kailash, you know, Pooja, you know all this.
Yes, sir.
It's
Yes, sir.
done in 4
The
to 5.
1 2th element should
Yes,
be 1
sir.
2.
Yeah, you're saying?
Yes, sir.
The matrix of A should be the transpose of what you've written. Because A21 should be second row, first column.
Yeah, you're right. Okay. So now, if I now take this expression and write it explicitly, even in more detail. So let us do it. You'll have Q, which is B comma T, sigma 1, sigma 2, sigma n. The first term is, let me write down one more term, sigma 2. This is how it is, isn't it? Anish.
Yes, sir.
So what will be the next term? Sorry, not next term, if I write it explicitly using this basis. You see the first term is going to be, this is fine? The first term,
Yes.
this one, this. What is the next term?
Sigma 2 M sigma 3.
And what is the, I'll have term like sigma n, let me write down, n minus 1 m sigma n, and then I'll have sigma n m sigma 1. Fine? If I write like this,
Yes.
are you
Yes, sir.
convinced? Are you convinced? Can I do little more, little better with this expression? If you remember your linear algebra or quantum mechanics course, you'll know. So in general, if I take this sigma I,
Projection operator.
yes, sigma I, and sum over I, what is the answer on your right?
Identity.
This is called resolution of identity. How many of you remember?
If the basis
Yes,
is
sir.
Go and check your quantum
Yes, sir.
mechanics.
CH 4 to 5 we have read this.
So now look at it. So let me change the color. The expression, you look at it. What is this? This part? What is this part? Sigma 2, you know, ket, then,
projection along sigma.
yeah, but sum over sigma 2, this is 1. Identity, isn't it?
Yes.
Similarly, I'll have another term here, no? Sigma 3. I have not written there, no? This one also will over sigma 3. This will also give you I, isn't it? So you will have many such I's, identity. So I can remove from, I have so many matrix element, I can just use the resolution of identity for all the spins. So what I'll be left to it then, if I keep on doing like this?
Sigma 1, sigma 1.
But something has happened. So actually, I have taken all the sum over sigma 1, sigma 2 to sigma n. So I have only sigma 1 sum left. The first term is there, sigma 1. What will be the next term? You see how many m's will be. So we'll be putting many m's next to each other, multiplying. How many will be there? Because if I remove, when you remove this m and this m will come next to each other, it will give you m square. So eventually, what I'm going to get, Anish, Kailash?
M power n?
Yes. It is m to the power of n. How many of you understand? And then sigma 1. Because this sigma 1 will be left, this sigma 1 will be left, all the others will be removed because of this resolution of identity, but all the m's will be next to each other and there are n such m's, so it will be m to the power of n. Is this clear?
Yes, sir.
And this is nothing but, since this is sigma 1, sigma 1, this is nothing but trace of m to the power of n. You know, trace of a matrix is the sum of diagonal elements. Okay?
Yes, sir.
So now my life has become not so difficult. No, it looks better. When you started, it looks better. But okay, I have to know the matrix M, isn't it? Now I go back and see what is the matrix N. I had told you the matrix M is a 2 cross 2 matrix with matrix element like M plus plus, M minus minus, M plus minus, M minus plus, isn't it?
Yes, sir.
It's fine. I hope it is not a very difficult thing to, the way I'm doing it is not difficult to follow. I hope. I am just hoping.
Yes, sir.
So now let me write down this explicitly. But before I write down this explicitly, I go back again. What is the matrix element? This one is the matrix element. Okay. So my matrix element was like this. Sigma I m sigma I plus 1 was exponential of beta j sigma I plus 1 plus b by 2. This is the expression, no?
Yes, sir.
So this is obvious, and let us call okay, obvious. Let me write down first. Exponential of beta, the first term is both are spin up, no? So the expression is going to be exponential of, let's look at it, beta times j plus b. Are you convinced? The first term.
Yes,
Because
sir.
1
Yes,
into
sir.
1 is j, and this 1 plus 1 is 2. This 2 and 2 will cancel, so it will give j plus b. What will be this one term? This one, m minus minus, is going to be exponential of beta j, because both are minus, means minus 1 into minus 1 is plus 1. But this one will become what? This one will become what? Tell me.
Minus b.
Minus b.
Yes. Why minus b? Because why minus b?
Minus 1 plus
Because this is
minus.
minus minus. This is minus b. What will be this? The off diagonal terms plus minus. This one will give you exponential of minus beta j, but this term will be 0, isn't it? 1 minus 0, 1 minus 1. And this one is also going to be 0. It is minus 1 plus 1. So what I'm going to get, exponential of minus beta j. Can you see this?
Yes.
Can you see this?
Yes, sir.
And let us call beta j is x and beta into b is y. Then this matrix I can write it simpler. It is going to be exponential of x plus y, exponential of x minus y, exponential of minus x, exponential of minus x. Okay, so far I hope this is fine. Now if you look carefully, this is an Hermitian matrix. You can check yourself. I'm not going to do it because it is done in 4 to 5. So his aim is Hermitian. What does it mean? It will have real eigenvalues. So one should be able to diagonalize it and should have real eigenvalue. And real eigenvalues. Okay? Just your quantum mechanics, same algebra. I am doing classical mechanics, these are classical spins, but I am doing using the same mathematical tricks used in quantum mechanics. Okay?
Yes, sir.
So now let us diagonalize this matrix, formally at least. So formally I can write that there will be an unitary matrix. I can do a similar transformation and I can I can write it as U inverse and then put this M U. This will give me a diagonal matrix which will be something like, I'll have two eigenvalues, lambda plus and lambda minus. Okay. Convinced? This is not very difficult thing to do.
Yes, sir.
Difficult thing to do. Now let us calculate. So essentially what is my partition function? My partition function is trace of m to the power of n, no? So let me write down trace of u d whatever, like anyway, like you can call it u d u inverse, or because it should be, because this basically means that u inverse m sorry, so if I write this, the d you can express what I'm saying, that m you can express as u d u inverse. I hope you understand.
Yes, sir.
Simple matrix algebra. Some problem with this. Wait for a yes. Some problem with just wait for a minute. But I hope you are following.
Yes, sir. Yes.
Because this is a model which is exactly solvable, and this is like hydrogen atom problem of
So
quantum mechanics.
will it come to lambda plus lambda minus power n?
Will come. Okay, let me write down here only. Okay, so basically your aim is U inverse, huh? But then whole to the power of n. Is fine? You follow from here, no? Because if you do U inverse aim U inverse, you get m, that is equal to U inverse, sorry, U D U inverse, isn't it? Because this is your D. Okay, so you put that here. What will happen to this? So this is nothing but you have U D U inverse into U D U inverse into U D U inverse n such terms, isn't it?
Yes, sir.
So now what is this? U inverse U, you know this is I. Okay. So what you are left with then? You are left with trace U again to your n U inverse. Okay. And since this is a diagonal matrix, you can write it as this is actually trace of a diagonal matrix. I just say that okay, if you can diagonalize it, then the trace of the diagonal matrix will be the eigenvalues, isn't it?
Yes,
Got
sir.
it?
Yes, sir.
Not the trace, the elements, the diagonal elements will be the eigenvalues. This is fine. And you have to take a trace of the diagonal. In order to calculate the Q, you have to calculate the trace of that diagonal of that matrix, which basically means the sum over eigenvalues. Now I'll ask you a small question. I think you should know from your matrix algebra or linear vector that if I have a matrix, the trace of a matrix A, trace of matrix A is diagonal matrix, which is sum of eigenvalues, no?
Yes, sir.
If you have diagonal matrix, it's also true for uh, non-diagonal. In that case, you have to diagonalize and then do it. So if I have a trace of say a square, can anyone tell me what is on your right hand side?
Lambda 1 square plus
Lambda 1
lambda.
square plus lambda 2 square plus.
Yeah, everybody knows here, no? It's very simple to see. If I construct a small uh, like this, here the trace is diagonal element, diagonal matrix 2 cross 2. A square is and this is going to be so trace of a square is so in general trace of a to the power of n is going to be what? Are you convinced if I write like this?
Yes, sir.
Okay, so your partition function is now going to be, but your matrix is 2 cross 2. There are two eigenvalues. So I'm calling it lambda 1 plus and lambda minus. Your answer is going to be this. Are you convinced? Tell me, Kailash, whoever is there.
Yes, sir. Absolutely.
So now what is our next task? Next step would be to calculate lambda plus and lambda minus. Calculating eigenvalues. How do you do this? Essentially, what you need to do, you need to do this, isn't it? So you have to have a determinant x plus y minus lambda This is fine. Is this fine? I'm going to solve a quadratic equation. Is this fine?
Yes, sir.
Yes, sir.
Should not be difficult. Let us do it. Expand it. Hmm. Fine. So you have lambda square, and this, if I take lambda common, like this, and this one is 2x. Fine. Now you remember that what is cos hyperbolic of x?
It's exponential x plus exponential minus x.
You remember this, no?
Yes, sir. Minus here.
So now I make use of that. This is lambda square minus what I'm going to do. I'm going to take exponential of x common here, which basically gives you, let me write down. Do it one more step. So this one gives you, this is 2 exponential of x cos hyperbolic y. Fine. And this one is plus 2 sine hyperbolic 2x. Fine. If I write like this,
Yes, sir.
I have a lambda. Lambda I should not forget. Okay. Now you go to your school days. Ax square plus bx plus c. I want to do it just to show that it comes correct. What are the roots? Fine. So in this
Yes.
case, what will be the roots? What is b here? B is minus lambda cos hyperbolic minus 2 lambda cos hyperbolic y, but minus. It will give you 2 cos hyperbolic y is your, not the lambda, 2 cos hyperbolic y, isn't it? That is your b.
P per x.
This fine? This is fine? Is this fine what I'm writing like this? But then you also have exponential of x here.
Yes.
Then plus minus b square within the root minus 4. So b square is exponential of 2x. 4 cos square hyperbolic y, and minus 4 is mean 4 is there. This 2 will give you 8. 8. A is 1. A is 1. So like this, huh?
Yes, sir.
Fine. So next step is lambda plus minus 1. This 2 will cancel. This will give you what? Now I can take 4 common outside. It will give you 2, na? This 4 from inside I take it
Yes, sir.
out. It will give you 2. This 2 and 2 will cancel. So you'll have, it will be left with exponential of 2x is fine. Is it fine?
Yes, sir.
Yes, yes.
But then I am going to use some other property of this hyperbolic function. This cos hyperbolic y can I express in sine hyperbolic? This one, this cos hyperbolic y square.
Is it 1 minus?
Not 1 minus, it is 1 plus sine hyperbolic square. Isn't it? Go and check. Is it 1 minus or 1 plus? Please do yourself and get me.
Plus I.
Check. It should be plus. So sine square. Let me write down like this. It's fine.
Yes, sir.
Now this 2 sine hyperbolic x is nothing but your exponential of 2x minus exponential of minus 2x. No. This is how it is, isn't it?
Yes, sir.
And this exponential of 2x and exponential of 2x minus 2x will cancel. So it will be left with, let me write down the first final expression. This exponential of minus 2x will be there, but also you'll have this. And this is the expression for the roots, the eigenvalues. You can check yourself. I think it's fine. Okay.
Yes, sir.
So let us proceed now. So now you can see there are two roots, lambda plus and lambda minus. Which one should I take? Because then your q is now given by this fine. But this is actually good approximation that if I go to the when n goes to infinity thermodynamic limit, I just neglect the second root, contribution from the second root. In the thermodynamic limit, why? Can anyone tell me why? Because if I calculate ln q, what will be ln q? Tell me. ln q will give you some because you take the derivative of that, you get different harmonic functions. Even minus kT ln q is your Helmholtz free energy. So ln q this is if I calculate 1 by n divided by ln q, and you will see that this is actually ln lambda plus 1 over n. You can do ln 1 plus. You can check, and this is lambda plus is much greater than lambda 1. The whole thing is lambda plus is much greater than lambda 1, lambda minus rather. So you can neglect this. So this is actually ln lambda plus. So that's why in the thermodynamic limit I can take only the first root, the first eigenvalue, the largest eigenvalue. Okay, and then what will be the expression for your partition function? Your partition function is going to be Anish and lambda 1 to the plus to the power n, which is sorry, it should be sine hyperbolic square y. A few places I have not written it properly. Check, huh?
in the 1 over n log 2 expression, the second term should be log 1 plus
Yeah,
lambda minus
it should be the
plus.
other way. Other way.
Yeah.
Yeah, I'll do it. This fine? I've done it. You can say I've done it. And if I put all the expression for y and x, this is going to be exponential of beta j cos hyperbolic. This is beta b plus exponential of 2 beta j sine hyperbolic square of beta b. This is your partition function. And your Helmholtz free energy is going to be, I'm not writing, you can just take a log of this, multiply with minus kBt, it will give you this, isn't it? I can write also. So your ln q minus kBt is your Helmholtz free energy, which is minus kBt ln of whatever is there. Now you have to take log of this, so you will have n here. Fine? This n will come. So you can see that other terms don't depend on your n. So it scales with n. This is fine. Your Helmholtz free energy. Now what I'm going to calculate now, which is very important, is called average magnetization or mean magnetization. And that people experimentally verify. The average magnetization you can always not matrix M. Here magnetization, okay? Same notation, but got it? Anish, Kailash and others. Same notation, but different quantities. So this is what is average magnetization. I have to take the spin, multiply this magnetic moment and add them, isn't it? An average over all realization, all possible arrangements. In one arrangement, some are up, some are down. Another arrangement, say I flip one of the spins. In another arrangement, I flip two of the spins. Like this, many such arrangements. Average over this. Okay, and if you do this, you will see this is actually del A del H at T, which is equal to 1 over beta. You can check yourself. It is not, I'm not going to do it because we have done same thing several times. Okay, and this is equal to n by beta, of course, d ln lambda plus dh, and this is equal to n mu d ln lambda plus by d beta mu h. Okay, which is n mu d ln lambda plus by dy. So what I need to calculate? I need to calculate the derivative. I take a log of lambda plus and take a derivative of that with respect to y. Okay, this is fine.
Small h here is
I told you in the very beginning that is small h. No, it should be here. A small h is this. B is h times mu.
oh okay.
Right. So now let us calculate this average or mean magnetization. It is n mu d dy of lambda plus, you see n is come here. So what is lambda plus? Let me write down. Log of lambda plus ln of e to the power of x cos hyperbolic y plus e to the power of 2x sine hyperbolic square y plus exponential of minus 2x. Now del del of this is 1 by log, no? 1 by the argument, which is okay. In the numerator, what I'm going to get, I'm going to differentiate this with respect to what? With respect to y.
Y.
And this is going to be exponential of x. If I differentiate cos hyperbolic y, get sine hyperbolic y, okay? Plus, this is like root over, no? N x to the power n minus 1. So, half x to the power n minus 1 means 1 over this. And then you have this. So this will give you exponential of 2x 2 sine hyperbolic y. Again, if you differentiate sine hyperbolic y is also cos hyperbolic y. No sign change. Plus 0. Fine? It is not very difficult.
Yes, sir.
This is n mu. Uh, so this is n mu, and then I was thinking, okay, let us do it. So I just these two and these two will cancel. See, huh? So you are going to get maybe I'll go to the other slide because you have classes now after this, but I want to finish this. I'll need 5 to 10 more minutes. Maybe I'll finish. So people who have classes, they can leave and they can see the recorded part, maybe 5-10 minutes more. Okay, not now at 7 you can leave. I may continue a little more today. Because it has become so heavy. Okay, I'm just thinking whether I can shall I stop here or so let me. So what I'm going to do, Anish, Kailash, Pooja, Nashid, whoever is there, I think I'm going to continue from here next day, which is on Thursday. I'm almost done. What
Yes, sir.
I'm going to do that I'm going to plot this magnetization as a function of temperature as well as a function of magnetic field and all these things. So which is going to take some time. So I think I'll stop here. because it is better that I proceed from here in the next class. So we'll start exactly from here. The
Yes, sir.
magnetization.
You need to revise a little
Yeah,
bit.
and then we'll continue from here on Thursday. Okay. Okay. So thank you very much.
Sir, there was a doubt.
Tell me which one.
So
Where?
why we had converted that line into circle?
Okay, because otherwise you cannot do analytical. It's very difficult to do if it's on a circle, if it's on a line.
Okay,
It's a
okay.
very,
Mm-hmm.
you have to do this analytically, and people do that actually because it's one trick. Use.
Sir, but computationally, people must have done for line also.
Yeah, computationally you can do, but I want to
So,
show you that analytically.
so
See,
the
in
result will be completely different, or
no, no,
what?
no, I don't think it will be different because you are in the thermodynamic limit when n is very large. In the thermodynamic limit, it should not matter whether you have a periodic boundary condition or not. Okay.
Okay, sir.
Yeah. So uh, so you'll see that actually there is something called two-dimensional Ising model, which is solved by Lars Zagar, one of the I think probably the best theoretical chemist in 1944. A very tough problem. I'm not going to do it. And in one-dimensional Ising model, will show that there is no phase transition, which we'll do in the next class. And then briefly mention two-dimensional Ising model, and then we'll move to something new topic, some new topic. Okay. So thank you very much for your attention.
Sir, I have
I,
one
Thank
question.
you, sir.
yes.
I'm not fully sure whether this is true, but if we evaluate m as a function of b and t, I mean, simplify this expression.
Yes.
At high values of b, will it be inversely proportional to temperature? Like I'm looking at the Curie law expression. Is that related or is that not applicable?
We'll see. The magnetization you're talking, no? You're talking magnetization.
Yes, yes.
So what happened that when you go to high uh,
Low values of
low
magnetic.
low temperature or high temperature?
High temperature, I think.
High temperature, it is. We'll show the expression. I'll show you the expression. We'll check whether it matches with Curie law or not. Okay. I'll show you exactly what happens at different temperatures.
Okay, thank you.
Okay, we'll do it in the next class because I don't want to skip.